Hello everyone, this is Dilip. In today's video, let's switch gears and talk about classification problem. Till now, we have seen linear regression, solving regression type problems. Today, we will see logistic regression, solving classification problems. Remember, I said earlier, there are two main types of supervised learning problems. One is regression problem, other one is classification problem. Till now, we have seen regression. Let's move to classification now. Logistic regression. So this is called regression for historical reasons. But the main purpose of this logistic regression is to solve classification problems. Let's move on. So what is a classification problem? If we have a set of emails and we are determining whether it's a spam or not spam, we call it a classification problem. In a similar manner, if here you can see the tumor sizes are plotted in the graph here, and based on the tumor sizes, we are determining whether the person has cancer or not. So the output is a predetermined set of classes. So if the person doesn't have cancer, let it be 0. If the person has cancer, let the output value be 1. Or for example, there can be multi-class classification problems as well. If you have a Gmail, you might have seen emails are categorized as primary, social, promotions. So this is an example of multi-class classification problem. For simplicity's sake and for better intuition, let's start with binary classification problem, where we know the output will be one of the two classes. So let's assume class 0 is the first class and class 1 is the second class. If I just tell 0 or 1, that also means class 0 or class 1. Now, given the tumor sizes, we need to determine whether the person has cancer or not. Let's assume the hypothesis will result in a value between 0 and 1. And we can put simply, if the value of the hypothesis is greater than 0.5, the person doesn't have tumor. The value of hypothesis greater than 0.5, the person. If we use linear regression to solve this problem, we might get a nice line like this. Then we can tell all the tumor sizes to the right of this line indicate the person has cancer. All the tumor sizes to the left of this line indicate the person doesn't have cancer. Now, what if we have one more tumor size in the test data, which is over here? This will result in our linear regression straight line to become like this. So as you can see, this particular tumor sizes indicate the person has cancer, but our line goes in such a manner that indicates that these particular tumor sizes people don't have cancer. And this is a major mistake. It should not happen that way. That's the reason a linear regression doesn't fit to solve the classification type problems. And one more thing is our hypothesis. So we need to transform our hypothesis by taking the hypothesis we already have in linear regression, and we need to make sure its value lies between 0 and 1 so that we can tell the person has cancer or not, or if it belongs to one of the two classes. If one value is, if the hypothesis value is greater than 0.5 or less than 0.5. So we need to modify our hypothesis function taken from the linear regression in such a manner that if its value is less than 0.5, it indicates it belongs to class 0. If it is greater than or equal to 0.5, it indicates it as class 1. So ignore this. This is a mistake. It should not be less than or equal to here. It's less than 0.5. Now, we know our hypothesis will look like this. H of x equal to theta transpose x, where theta is the parameters and x is the variables. Our hypothesis can be simply represented in this manner. Coming sigmoid function. So the term sigmoid or logistic, both are same. So that's the name, that's the reason this got the name logistic regression. So here the intuition is very simple. Just to take theta transpose x as z and you fit it into the sigmoid function. Sigmoid function is nothing but g equal to 1 by 1 plus e to the power of minus z. Now, you take any value of z, this function will make sure it will be, the value will be transformed in such a manner that it will be between 0 and 1. So this can be also written as 1 by 1 plus e to the power of minus theta transpose x. Now we can use g to determine whether our equation will fit class 0 or class 1. So this is how a sigmoid function looks. Given as z of z looks like this. And one thing you can see is if z is less than 0, you can see z of z is automatically less than 0.5. And if z is greater than 0, z of z is greater than 0.5. So I might use hypothesis and z of z interchangeably, but you can see the intuition here. But so here our z is nothing but our hypothesis. And as our hypothesis is a negative value and it approaches negative infinity, g of z becomes 0. And as our hypothesis becomes greater than 0, and if it approaches plus infinity, z of z approaches 1. So we can take this as a final indication whether the given variables will make it go to class 0 or class 1 given a theta. So this is our representation. So what does the transformed hypothesis value indicate? So transformed hypothesis means nothing but g of z. So the g value indicates probability that given our hypothesis equation parameters by theta and a variable, it gives the probability that it belongs to class 1. Now, if you know about probability, you might already know if a given equation or a given function, if it results in either it belongs to 0th class or 1 class, either of the two classes, adding the probability for the two classes will give you equal to 1. So if you want the probability that the given variables will result in the class it belong to class 0, you can use 1 minus probability of it becoming class 1. So how to derive the parameters theta and all we'll see in the next video. Now let's go much ahead and let's see how the plotting looks like. So there is one more term called decision boundary. So we have two classes here. Let's assume they are class A and class B. Okay, let's just put class A over here and class B over here. Okay. Now, given a variables x1 and x2, so it's a value of two variables x1 and x2. So given two variables, how do you determine whether it belongs to class A or class B? Let's suppose we derived the values of theta and we got the values like this. So theta 0 minus 3, theta 1 is 1 and theta 2 is 1. Now, this will give us our hypothesis. Now, remember, I was telling earlier, if our hypothesis is negative, it indicates it belongs to the first class. If it is positive, it belongs to the second class, positive or equal to 0. So same thing, if we apply over here, we will see putting these values into this equation and making them greater than or equal to 0 will result in x1 plus x2 is greater than or equal to 3 and x1 plus x2 is less than 3. The first one indicates it belongs to class B. This indicates it belongs to class A. Now, if we just put x1 plus x2 equal to 3, which is looks like a boundary, and if you plot it x1 plus x2 equal to 3, we get what is called decision boundary. Now, all the hypothesis results, which will result in a value getting in. So you can assume that hypothesis values will be in a different dimension. So it's not like x1 and x2 values here, but they will be in a different dimension. But for simplicity's sake, those are plotted here. And if we get the hypothesis values that cross this decision boundary, we take them as class B. And if they are below it, we call it class A. And we'll see more about this decision boundary later on in the next slide. Okay, so here we talk about nonlinear decision boundaries. Remember, we talked about polynomial regression earlier. So same thing can be applicable here also. That will help us give nonlinear decision boundaries. So if you have a one class belonging like this, class B belonging like this, and class A circles belonging like this, it's not possible to fit a straight line into this data. You need a nonlinear decision boundary. So for that, what we do, say we got the results of theta. So how we derive theta, we'll see in the later videos. But let's say we derived the theta. We'll get the values like this, where theta 0 till theta 2 are all zeros, and theta theta 3 and theta 4 are ones. Now this will give us x1 square plus x2 square. And if x1 square plus x2 square is greater than or equal to 0, it belongs to class B, and if less than 0, it belongs to class A. So I just put 1 and 0 here, but these are actually, this is class B and this is class A. Okay. Now x1 square plus x2 square, if you just put equal to 0, it's a circle. So it is in a circle like this. Nice circle. You can see it fits our data well. Now, if we take much more complex polynomial equations, this will result in much more complex decision boundaries. The decision boundaries might look like this. It might look like it might give us a nice ellipse like this, or it can be like this, much more complex. It can be like this. Okay. So based on the order of polynomial we take, the decision boundaries will be much more complex as well. That's it for today's video. Thanks for watching. Bye.